Okay, welcome to the lab number 2. Okay, in this lab, we're going to model some of the digital circuits. Okay, uh, in all three modeling styles. Already we have seen what are the different modeling styles that we have here. Okay, uh, let us take some example. For example, addition we have already seen, right? Okay, we'll take a 2x1 multiplexer, modeling of 2x1 Mux. Okay, let us recap what we have learned in the previous class, right? Okay, if you want to model any digital circuit, as we know that essentially we have three modeling styles, right? Okay, what is the first one? Can anyone help me? What is the first basic one? It may be a data flow modeling. It is very simple. Okay, data flow. What about the second one? It's the structural. The third one, behavioral. Right? Okay. Today we are going to model this 2x1 multiplexer by using all these three modeling styles. Okay. Let us see how to do this one. So what is the prerequisite if you want to write a Verilog program in general? We should know what is the external view, and then we should know what is the internal view. Okay, so let us take a 2x1 multiplexer. What is this 2x1 multiplexer means? What functionality it will do? It takes two inputs. Okay, it selects one input transferred as an output. Okay, based on the selection line, right? Let's take something like this. Okay, so let us consider this is A is one input. A is one input and B is another input. So either input has to go as an output or B has to go as an output. That's depending upon selection. If the selection line is one selection line is sufficient to choose one of these two input lines. Okay. If the selection line is equal to 0, for example, if it is 0, it will choose, for example, A will be selected as an output. If selection line is equal to 1, for example, then it will select B as an output. Okay, this is the logic. This is what the logic behind the 2x1 multiplexer. Agreed? Okay. Now, this is also we can call it as an external view. Okay, having some two A, B, and S are the variables, and Y is another variable we are using to define this 2x1 multiplexer, right? So shall we write the program for this one? How do we start the Verilog program? It will start with module keyword. Okay. Let us give, what is the name of this module? Let us give as simple as that mux underscore 2x1. Okay, simply. Okay, you can write it anything, but what is the precaution that we have to see? We have to consider. You should not start with number. That's the only thing you have to remember. Okay, don't try to attempt to write a 2x1 multiplexer. Okay, 2 is a number, so you should not start with number, right? Good. Okay, therefore, let me write here is mux underscore 2x1. Okay. Why I've written a small m here? because Verilog is actually every keyword is started with lowercase letters. That's the reason why I am also writing the lowercase. But if you are interested in writing the uppercase letters, definitely you can write it there. But the same names that you have to give wherever it is possible, right? Okay. Now, what are the things here we should see? What are the variables we have used? A, B, yes. A, B, yes, and Y. Finally, somewhere we have to end this program. Let me write the program in this way. And module. Okay. So therefore, this is what the main part of writing the program. So, and one more thing I want to introduce here is, since we are writing the same functionality in three different modeling styles, that's the reason why I want to give a specific name to represent which modeling I have used. For example, if I want to use the data flow modeling, just simply I want to write here is a data modeling somewhere, data flow modeling somewhere. Somewhere I can write here is DF. Not necessary. I'm saying that. Okay. For sake of your understanding. Okay. Right. If it is a structural modeling, what I can do? Underscore SM. Okay. But data flow means better I can write it in this way. Names will be very good in this manner. DM. DM stands for data flow modeling. SM stands for structural modeling. BM stands for behavioral modeling. Something like that. We can write it, right? Fine. So now we have used the three variables. Okay, four variables we have used, but we should say what purpose we have used those variables. Okay. We have used it for A and B for input, right? So therefore, we have to write the put declaration. Input A comma B comma yes. All these three are input side, right? All these things are related to input because we have to give what is S, what is A, what is B. We have to give whenever we are giving, that is called inputs. Whenever you are taking, those things we can call it as an output. We are not going to, we are not evaluating actually what it is, why, but logic is, so the circuit is providing the output. Okay. Then we are taking that output. Whatever it is giving, we are taking that output, right? That's the reason why it is an output. Okay. Let us take output Y. Can you differentiate? I'm using the different colors. Input purple I'm using, and A and B and S and Y are I'm using the black color. That means whenever I'm using the black color, it means that the user defined one. Okay, you can write any names for that. Any variables that you can take it, you can take it. Right. So what is the prerequisite for the data flow modeling? What is the prerequisite for the data flow modeling? What we should know if you want to write data flow modeling. Boolean equations are required, am I right? Boolean equations are required. What are the Boolean equations that are responsible to get this particular functionality? Generally, Boolean equations are come from the truth table, right? Am I right or not? Okay, that is what the practice that we have learned from the BTech course, BTech course onwards. Right, we take that one. Okay, how do we generate the truth table? S is one input, A is another input. I'm so sorry. S and Y is only the input output information. Okay, if S is equal to 0, what should be the output? A. If S is equal to 1, what should be the output? B. Now simply, Y, how can I written Y? Y is equal if S bar dot A or if S with B. Okay, right. So therefore that equation I need to write it here. So how do I write this equation? With the help of assign keyword, right? Assign y equal to, how do you write bar? Bar is actually a the Boolean operator, right? But in Verilog operator, we have to write the bar. That we have to represent it by negation, something like this. Not of yes. How the dot will be replaced with in Verilog? Ampersand and yeah. So this is the one word actually we can consider this. Okay. So we take this is something like this and take or with what? S and B and use semicolon. Even if you're not writing the brackets also, it's not a problem. But we give the preference to what it will be available first, and it's of readability purpose. I have written this one, nothing more than that. Okay. Even if you're not writing the brackets also, it will work. But you have to evaluate output properly. Okay. But of course, which operator will be executed first? The preference will be there. Okay, from unary to ternary operators will be there, but the preferences will be there. But I'm not going to go more detail about it. Okay, simple statement I have written on this way. Any question so far? Output register. Okay, it is actually relevant for behavioral modeling, not for data flow modeling. It's simply by taking the input. The moment if you are in applying the input, the circuit will be evaluate that input and produce an output. Okay, the output is not able to store any kind of information. Okay, the moment if you want to store the information for somewhere, for some particular reason, we have to use the register there, right? Okay, we talk about little bit later on that, right? Okay, similarly, can we try to write the structural modeling? Okay, so let us write the structural modeling. I hope let us copy this program. Copy this program and then paste here. Right. Now let us write. We have to. Is there any change in the external view? Even if you are changing the data structural modeling? No, because external view is the same. It always tells you the input output information. But internal view can be changed, right? That's the reason why we are going to remove this part and we are going to write the structure of the logic functionality. Okay, how do we get the structure of a logic functionality? From the Boolean equations. Okay, so we take the Boolean equation. Okay, already we have seen that Boolean equation and we have to develop the circuit. So what is the circuit of this one? Something else we write, right? So let me consider this is S here. Okay. And S bar is also there. Right. Okay. Next, we need to have how many AND gates? 2 AND gates. And how many OR gates? 1 OR gate is sufficient. One OR gate is required. Okay. So the output of this one connected here. The output is connected here and take a common. Okay. So what about the inputs for this one? Here S bar is required. And then A input is also required. Next, but I want to take the another color. Okay, better I have to take the blue color for this, green color for this, and this also, and this is the C only, A here, B here, S is one input, Y is my output. Okay, this is what the internal circuit, right? Okay, let us write a Verilog program for this. Externally, we don't have any changes, but internally there is a change, right? How many gates that we are using inside of it? How many gates we are using inside of this structure? 4 gates. Okay, we have tried the 4 gates in here, right? Okay, that's the reason why I'm going to take this is a little bit for. Okay, now, so let us write the name of the gates, right? Let me write the name of the gate is Z1 here, Z2 here, Z3 here, Z4 here. Okay, so whenever you write a structural modeling, first give the name of all the available components or the gates, right? We have to call gate by gate. Okay, what is the first gate? Let us write not gate. Let us write. So not means NOT not is the keyword that I have to use. What is the name of the gate? G1. Okay. So whenever you write a gate statement, the gate statement is also called as a gate primitive statement. What is this? What is the meaning of the term? What is that? Gate primitive statement. That means the output we have to write first of that gate, and then we have to write the inputs to that gate. What is the output for this NOT gate here? You can see. Do you see any output here for this one? So the input is coming. Undoubtedly, we can see that input, right? So input S is we have already given. What is the output here? Is there any name for this one? There is no name. There is no name, right? That's the reason why we have to give the name. For example, this is SB. SB stands for S bar, something like that. It is a S bar. Or some write X also you can write, Y also you can, whatever maybe you want to write, you write it there, except number. Okay, okay. So therefore, I'm going to write SB here, and this is the output of that gate. And what is the input of that gate? Yes, right? Okay, similarly, for the gate number 2, what is the name of the gate? Gate number 2, AND gate, right? We need to write AND. Okay, what is the name of the gate? Z2. Now, what is the input and what is the output for the gate 2? Can you see any name for the gate 2 output? Let us write a name for that one. Let us give, for example, this is X, let me consider it. This is, okay, X already, Y I have already given, right? Okay, let me write in this one. For example, W1, Y1, Y2. Instead of calling it whiles here, people will call it as a net. Okay, let me take this the same notation, N1 and N2, net 1 and net 2. Net 1 and 2 is nothing but Y, right? Okay, so let me write here is N1. Next, what is the input? A input, B input, right? Sorry, what is the one input? A. Next one is SP. Okay, see, if you write SB first and then A, does not have any problem. Okay, but the first one must be output, then all the inputs can be written. So interchanging of the inputs is not at all a problem. Are you getting the point? Right. Next, we take another AND gate. We have another AND gate, G3. This is called N2.
This is B, and this is S. Finally, we have an OR gate that is called G4. What are the variables for this one? Very good. It's Y, comma, N1, comma, N2. That's it. Okay. So far, so good, right? But you have written what A and B and S and Y you have written, and you have declared. Those are all the port declarations we have already done. But what about the SB, N1, and N2? Okay, we have to define them also. So since these variables are inside of your structure, that's the reason why we have to call it as a Y data type variables. Y data type variables. Y is actually net data type, and it is come under the net data type, but it is actually the Ys, right? Okay. So we have to declare them also properly. Okay. So below the output, we have to write Y. Okay. So now Ys are, that is also keyword Y. What are the Ys here? N1, N2, and S2. Is the point is clear to everyone? Okay. So now I want to change this modeling style as a SM, right? SM, structural model. Now let us write the same thing in behavioral as well. Okay. Right. Please help me. What things that I should remove in this particular program? Anyone? What is irrelevant information in this program? For the behavioral modeling, what is irrelevant? Internal structure is irrelevant, right? Okay. So therefore, all these things are related to structural modeling. So hence, I'm going to remove everything. Okay. Right. But what statement I have to use here? First of all, always block that I have to write, right? So I need to write always here. Always at the rate of. So that means the sensitivity list I need to write here. What we need to write? Sensitivity list, right? That means what do you mean by sensitivity list? The variables which are responsible to change the output. The variables which are responsible to change the output is called sensitivity list or sensitive variables. Am I right or not? Okay. So the output is changed on what variables? The inputs usually, right? If the input is changing, output will changes. If the input is not changing, output cannot change, right? That's the reason why by default, normally we can call it as inputs are sensitive variables or sensitive variables, right? We can write here is S is one sensitive variable, A is one sensitive variable, B is another sensitive variable. That means at the rate stands for whenever there is a change in S, A, or B, or simultaneously all these three are changing, then definitely a particular block, okay, whatever the beginning block is there, this block must be executed. Is this one we have learned previously, right? Right. So the moment if I ask you to write the behavioral modeling is everything that should come into your mind is I have to write the always block first of all. Okay, within that always block, I need to write the Verilog program. Am I right or not? Right. Okay. Now, what kind of statements we have to use here? Procedural statements, right? What statement we have used in data flow modeling? Assignment statements. What statement we have used in structural modeling or gate level modeling? Gate primitive statements we have used. And what statement we are going to use in this one? Procedural statements. Right. What are the procedural statements? If statement, if else statement, case statement, for loop. Almost all the C language constructs we can be used here. Majority of the things we can use it here. Okay. So for the simplicity, I'm going to use only if statement, simply if statement. Okay. Can somebody help me? What is the if statement here? As you know very well that you know, I'm going to take this particular information and then copy somewhere. Since it is relevant here, so I'm going to copy and paste here. Okay, so I'm going to remove this particular portion. I don't want this particular one, am I right? Okay, this is not at all relevant for us. Remove that portion. Okay, what we need actually, we need a truth table for this one. Okay, this is what simple input output behavior, right? Keep it here. Okay, okay. It is a simply input output behavior only. Okay, if S is equal to 0, Y becomes 1. Okay, if S is equal to 1, Y becomes B. Right. Okay, that information we can write it in the form of a textual information, something like this. If S equal to S equal to 1 bit of 0. Okay, this is how we need to write. Equality stands for double equal we have to write, not single equal. Single equal in Verilog represents assignment. Okay, in the data flow modeling, what we have seen, okay, that means Y is assigned with the evaluated value. Okay, so here the single equal to stands for assignment, double equal stands for comparison. Double equal is for comparison. So equality comparison in this case, right? Okay, here if S is equal to 1 bit of 0, that means S is equal to 0, what should be the Y? Y equal to A, as simple as that. Whatever A variations that are there, that variations will be reflected on Y, Y, or Y net. Okay. Else, if this is not the case, then what we have to do? If this is not the case, else means that if S is not equal to 0 means that it can be 1 or any other thing for any other case. For any other case. What about this one? Y equal to D. And finally, and this particular block. Hopefully you catch this point, right? Right. So, but one important thing that we have to remember, whenever you're writing the structural modeling, because internal weights are need to be represented by Y data type, right? Similarly, whenever you write a data flow behavioral modeling, all the outputs, whatever the outputs you take, all the outputs are represented by a registered data type. Will it write? Registered data type. Okay. Reg we have, right? Reg Y we have to. Don't forget to write a registered data type, right? This is how we have to write a Verilog program for any digital circuit. Okay, essentially we have data flow modeling, which can be modeled by using Boolean equations. Okay, or we can call it as assignment statements, or either by using the structural modeling or a gate level modeling also we can call it as. There we have to use a gate primitive statements we have to use, or either we have to use, or we can use either behavioral modeling. Okay, behavioral modeling is we give the input output behavior in the form of a truth table. Just we can write it simply. Okay, is that point is clear to everyone? Did you find any difficulty in this one you write in the program? Right. Okay. Okay. Now, so the first part is over. Now we want to simulate this one first of all. Okay. If you we have written the Verilog code. Okay, somehow we have modeled that one. Whether it is working correctly or not, how do we know that one? Okay. For that, we are going to apply the input signals to it and get the output for that. Okay. So now let us write the test bench for all these three models. Okay. Right. Better I want to remove this particular one. I want to keep it as a data behavioral model. I'm so sorry. Let me take a small letters only. Behavioral model. Right. Now let us take the test bench for this one also. Okay. So test bench is nothing but just giving the necessary input signals to your logic diagram, so logic circuit. Okay. So for example, if this is your logic diagram, okay. As you know very well that we have, what are the inputs here? A, and this is called B, and we know that S is available and it will produce Y. Okay. So this particular logic circuit can be modeled by any means. Either data flow you can do it, or behavioral you can do it, or structure also we can do it. Doesn't matter. But the inputs that we are giving is the same, right? Okay. Our requirement is that we have to give somehow the inputs to this one. This block has to give input A, input B, and selection line S. Okay. And it will produce an output Y from this one. Okay, right? So therefore, we have to give this as a test bench. Okay. How do you give A, B, and S? That's the question. Okay. Okay. So as we know that, see, the simplest form that we have given S and Y something like this in the previous case, right? Okay, 0 we have given, 1 we have given. That's the reason why A here, B here. But the full form is not like this. Okay, what is the full form actually? If yes, if you give S, A here and B here also we have to do, right? And then we need to calculate Y. If S is equal to 0, that means three variables that we have to consider, right? Three input variables, one output variable. If three input variables that are there, how many possible combinations we have to apply? Sorry, how many possible combinations we should apply? 8 possible combinations. Okay, but all the 8 possible combinations, I have to see what is my output is. Okay, so 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1. I'm sorry. This is what is this one? 1, 0, 1, 1, 1, 0, 1, 1. Can someone help me to figure out what is the output of this one? If S is equal to 0, what will happen? For all this S is equal to 0, what will happen? A will be the output, right? That means this will be the output, right? Okay. Therefore, the output will be 0, 0, 1, and 1. Am I right? Now, if it is some other case, for example, this one. For example, this one. For S is equal to 1, B will be the output. Okay, therefore, let me write this value is 0, 1, 0. Like it. This is what the input we have to give. Okay, what is the responsibility of this test bench? The responsibility of this test bench is it has to produce what is A, B, and S to the design under test. Okay, this is what the design under test, right? Okay, so therefore, that means instead of writing something like this, we have to call in this way. Okay, so test bench is considered as a top module. Test bench is considered as a top module. Okay. Okay, so that means it has to generate what? It has to generate A signal. It has to generate B signal. It has to generate a signal, and it will take an output Y. Okay, what is the responsibility of the test bench? It has to generate the necessary input signals to test the logic, right? Now, if I ask you one question, do we have 3 test benches to test 3 modeling styles? Not required, right? What you put inside of this one is doesn't matter to you. What is required for you as a test bencher? How you are giving the input to that module is important. How they have written the code is irrelevant to you, right? So whether the input pins are there or not, we have to check it. Whether input pins are there, give the inputs to that pins. Okay, and then verify whether it is working correctly. Okay, so that's the reason why, whether it is a data flow, whether it is a structural, whether it is a behavioral, the test bench is only one. It's the same. Only one test bench for it. Right? Good. Okay, let's go and write the test bench for it. Okay. Can you recall once what I have written in the test bench in the previous class? What I written? Module. Next. Mux underscore 2+1 underscore DM, not DM, in fact, for anything, underscore test. Okay, I should not write input and outputs here. Okay. And finally, what I have to write? Finally, I need to write end module. Somewhere I can write the end module. Because I don't want to forget what I write here. And module, don't give the space between the end and module, and then semicolon, so not required, right? So inside of it, I need to write what I have to write. Just I can simply, for simplicity, I'm going to do just to copy and paste this information. Okay, the input output behavior. Let me put somewhere like this here. Just only the input and output information. So now, can you please tell me how you can change the inputs? It must be a register. Very good. It must be a register there, right? What about this one? Y data type, right? Y. Very good. What is the third step that I have to write? Module instantiation. Which module that you want to instantiate? You would like to instantiate data flow modeling, for example. Okay, let me take this data flow modeling. Okay, copy.
and then paste here. Okay, since it is a one instance to this particular text bench, we have to give the name of this instance. Okay, like G1, G2, whatever we have given, the same thing that we have to give. Here, let me consider this is simply a module, right? Okay, let me write this is this is M0. Let me write this is the M0 component. Okay, right. Now we have to write the test patterns inside of our test bench. Okay, what kind of statement we have to use to do this one? Initial, very good. Initial. Let's begin here. And then, you know, let me write the end here at this point. Okay. Now, how do we give this particular information? S is equal to 0, semicolon, A is equal to something like this. Okay, let me write in this way. Look at everyone. Carefully just observe me what I'm writing. S is equal to 0, A equal to 0, and B is equal to 0. Okay, something like this I'm writing. This is the one way. After 1 nanosecond, for example, what about at 1 nanosecond? At 1 nanosecond, S is equal to 0, B is equal to 0, and sorry, A equal to 0, B equal to 1. Like this, I can write all the 8 possible combinations. You know very well about it, right? But a small modification I'm doing here. Okay. Instead of writing something like this, I can also write this way also. At another 1 nanosecond, I'm using one operator called concatenation. This is called curly braces. We can call it as concatenation. Concatenation means we are grouping the variables or grouping the bits as one. Okay. So therefore, what I'm going to do here, S comma A comma B. I'm going to group them. 3 individual bits, I'm grouping them as a 3-bit variable. Okay, something like this. 3 bits I'm using, that is 0, 1, 0. Now the first bit represents the first bit. MSB is representing the S. Next one, A. Next one is B. So this is the S is actually the first. So this is first one is relevant to this information. This one is relevant to this information. This one is relevant to this information. So you get to the point? Otherwise, what we would have written? S is equal to 0, A equal to 1, B equal to 0. I would have written. So something like this is very simple when compared to the previous one. Just only for reducing the complexity of writing the code, nothing else in it. Are you get to the point? Okay. Now, similarly, we have to write or 3 times I want to copy and paste, a number of times I want to copy and paste that one. Okay. So do one thing. Let me do one thing. Okay. I'm not going to use this particular approach at this point of time. I want to skip to another one. Since I want to write some another way also. Take this one. For example, this is what A, right? Okay, copy this. How many times let us copy this? 4 times, like 3 times I want to copy this one, paste this one. Okay, therefore this is the one. Another simplest way I'm writing here, right? Okay. As you can see here, this is the one. This is also one. Look at this one. At 1 nanosecond, A is equal to 0, sorry, S is equal to 0, A is equal to 0, B is equal to 1, right? At 2 nanoseconds, what will happen? S is the same, A is also same, but B is changed. Okay, let me change this one also. I didn't change this one, right? I need to change this one. What about this one? This value is 1, 0. This value is 1 and 1. Okay, what is the difference between these two? Can you tell me? Which one is changing? S is same, B, A is same, but B is changing. But what is the difference between these two? S is same, but B is changing, A is changing, B is also changing. What about this one? Only B is changing, right? If something is not changing, then don't mention that one, not need to write that. Okay, so that means, let me write in this way. Okay, if A is not, S is not changing, don't write that one. If B is not changing, don't write that one, because up till one nanosecond, S is equal to 0, A is equal to 0. If you're not changing that value, means that that will be continuous. If you're not changing anything, means that it will be continuous to that particular time slot. Are you getting the point? Okay. So this is another way of writing this particular one. What about here? Which one I can remove at 2 nanoseconds? I can remove S, right? Yes, very good. But is it possible to remove A and B? No, because they are changing, right? Okay. So therefore, at the 2 nanoseconds, the values of A is equal to 1, B is equal to 0. Okay. What about at the 3 nanoseconds? Which one is not changing here? Which one is not changing? S is not changing. A is also not changing, right? So we have to remove. Okay, only the changing variable is B is changing something. Okay, this is another way. Conventionally, you know that everything that you have tried from 0 to 108 nanoseconds, you can write each and every change that you can. But little bit intelligently, what we have tried, this is the way that we have tried. Okay, another one is fine. Okay, next one is what? Let me write another 1 nanosecond, because remaining things that are also there, right? Okay, from here I'm going to write S comma A comma B, for example. Then I can write 3-bit of 1 0 0 0. Okay, sorry, these many bits are required. Okay, but in this case, we have no choice that we have to reduce that value. Okay, since we have combined them as a 3-bit number. Okay, obviously you have to rewrite the 3-bit number only, undoubtedly. But in the previous case, it's not that, right? Okay, let me copy this one. How many times? This is the one time. This is the second time. This is the third time. Okay, so here there is no option that we have to take. We have to write all the possible combinations. This is another, the simplest way. 1 0 1 1 1 0 1 1. Right. So finally, for another 1 nanosecond, for example, another 1 nanosecond. Okay, the dollar stop. Let me write the system task here. Dollar stop. That means at the 9th nanosecond, the simulation will be terminated or stopped. Okay, hopefully we have written everything, right? Okay, if you want to test behavioral modeling, what do you have to do? If I ask you to simulate the behavioral modeling, okay, so which part of the test bench you have to concentrate now? Remove which statement? We have to remove this statement, right? We have to remove this statement and then copy paste the required modeling. Instead of the data flow modeling, what you have to do? Behavioral modeling name that we have tried. Remaining as is, no change at all. Nothing changed. Only thing is that module name must be, module instantiation must be changed, right? This is how we have to write the Verilog program, and this is how we have to write the test bench. And now we are going to simulate this information. Okay, we stop here now.